Engineering geology is basically using geology to inform engineering practice, so it's looking at stuff like soils and rocks, kind of analysing their different properties, and kind of looking at and advising how they're used in construction. But it's like wide-ranging. It can also be things like looking at contaminated land, kind of environmental factors. I started off doing natural sciences as an undergraduate at Durham, and I did biology, earth sciences and archaeology. And I did mostly earth sciences and then worked for 2 years and then came into the masters here. So to come and do it at Newcastle, you needed an upper second class honours degree from a UK university or like an equivalent from an international institution. But a lot of people who come in to do the course I did, so the MSc course, actually came from industry, so it's quite a vocational one. It's like if people have got experience doing that sort of thing, you can come and do the course in it as well. It's quite a lot of maths, but it would mostly be things like mechanics, so working out forces and momentum, which I guess ties into physics, like that you kind of do some rock physics. You're looking at forces and pressures and stresses and stuff like that. But yeah, I suppose most of it is geology based, and but there's a mixture. If you do contaminated land, there's chemistry and biology sometimes as well. The first thing I'd say is like to do it as a course and then to do it as a career, mostly just hard work, because there's a lot of hours when you do an engineering degree and when you work in engineering. But you have to be really practical as well, because I think it's quite often, stuff will go wrong and you have to think of solutions on the spot. But like all the usual stuff as well, like you have to be literate, you have to be definitely numerate, because there is a reasonable amount of maths in it. Not really good. No, it's not like physics, or I think it's probably that you do a lot of mathematical stuff every day. It's, I suppose, like applied maths, so it's kind of maths of stuff that you can see. For me, it's easier because it's all looking at how rocks fall and how things fit together. What I'm doing at the moment is I'm doing a PhD, so kind of after my engineering geology course, I kind of started doing a bit more like geochemistry, and the main thing that it will contribute to sustainability is reuse of waste. So using like industrial wastes for actually capturing CO2 out of the air. So there's like a kind of double-edged thing in it, I suppose. There's actually like the CO2 capture and the kind of environmental climate bit, and the kind of structural reuse of waste. Everybody has like a different take on this. I mean, I guess the broad understanding and the kind of scientific understanding of it is that we produce a lot of carbon dioxide mostly, but there's other compounds obviously do this when we burn fossil fuels, and various industries and things like construction do it as well. It's going into the atmosphere and it's getting to a very high level, and it's likely to be doing or to start doing nasty things to our climate. So it's pretty pressing that we do something about it. You can get into so many things on this. The carbon capture and storage, you have, like in a natural system, you have different places that store carbon. So like, you look at a carbon cycle and you have different places that store, and then you have fluxes between those stores. Like the most recent methods, a lot of them are looking at things like afforestation, so planting more trees, which is quite a simple one, from everything to what I do, so enhancing soil carbon capture and storage, to the potential that the oceans have to store carbon, what they're doing now, could that be enhanced, right down to the really kind of like engineering kind of physical solutions that you see in the news of things like artificial trees, which use different kind of chemicals or special polymers to kind of capture it out of the air and dispose of it. You can't really. So this is the thing. So all of the sinks have different capacities. So like the ocean sink is enormous, like it's really, really massive. But the soil sink is really big as well. But they have different fluxes. Flux from the soil to the atmosphere is really big. So that was one of the things that, like, when we started doing this work, we were like, okay, so the sink isn't as big as the ocean, but the flux is huge. So it's like, if you could harness it, then that would be really cool. I don't think my research is really dangerous, but then I was like, I spend quite a lot of time on steelworks and I've been sort of mining things and stuff like that. So I mean, you're kind of around like molten metal and big vehicles, and I guess that's pretty dangerous. But I guess like the most dangerous thing is probably on summer school. So I went on a summer school last year, and we ended up going whitewater rafting, and we met 2 bears, like just in the wild in Canada. So it was like, that's probably pretty dangerous. I'm finishing my PhD really soon, so I'm due to finish in April next year, and that's kind of the end of this bit of the project, I suppose. But I'd quite like to carry on. But I think actually I have quite a lot of interest in science education and also science policy, so I think I'd probably be wanting to look at how what I do is actually used like in the real world and how it would be developed as policy within the government. I think it's really varied, and I think it's an interesting subject, so you get to do a lot of different things. It's not really focused, it's not sort of narrow, you get to look at all kinds of different topics. And it's really useful, and it's quite vocational as well, I suppose, if you have a passion for construction or building structures or geology, or it's really hands-on, and you get to see stuff that you've designed and see stuff that you've built actually happen.